Okay, so today we are starting the topic of random vectors. Okay, so previously we have discussed the case of two random variables. Let's say that previously two random variables such as x and y have been discussed and the linear dependence, let me put in quotations, between x and y has been specified or quantified, you may say, in terms of covariance slash correlation. So if you have zero mean random variables, they are the same, okay? But this is the concept, covariance or correlation of x and y. Okay, now let's assume that I have not two random variables but n of them. So this is right now the vector x, and the vector x contains x1, x2 and xn, n random variables. So what's the meaning of this? So previously I had only two, now I have n of them. So how can I characterize this random vector? You can immediately say the following. Now, joint distribution of n random variables is needed. Indeed, you are right. If I have two random variables, I need a joint distribution of these two, let's say. If I have n of them, so I need to understand their joint distribution, meaning that this is the marginal distribution for x1, then the pairwise distributions x1 and x2, x1 and xn, okay, but all of them are contained in the joint distribution x1 to xn, because by marginalizing this joint distribution I can get the individual marginals and pairwise distributions and so on. Okay, so how about this? So let's define, well, this is difficult to achieve in many problems. So let's define, let's say, correlation matrix for a partial description. Okay. So what do I mean by that? So this will be Rx. This is the correlation matrix. Well, let me define also Cx over here. This will be the covariance matrix. Okay. Now I will define two matrices. Correlation matrices, so this is R, this is C. Expected value of x vector y transpose. Okay? Or x transpose, sorry. I have this x over here, x over here. And this one is expected value of x vector minus the mean of this x vector mean of this x vector transpose. Again, if you have zero mean vectors, so what's the mean of a vector? Mean of a vector is another vector where this expectation is evaluated at every entry. Okay, this is called the mean of this random vector x, where you evaluate the expected value of x1, expected value of x2, and concatenate them. Okay. So how can I do this calculation? So let me do this. So this is expected value of, this is x1, x2, xn, and x1, xn, as you see. Okay, I get something like that. So if I do this calculation, what do I get? So I get a matrix over here, obviously. Then I take the expected value of every entry of this matrix. So I get expected value of x1 square. Expected value of x1 times x2. Expected value of x1 times x3. And the last one is expected value of x1 times xn. Okay? So similarly, x2 times x1. So this is the first column. This is the last entry of first column. Okay. And it goes like this. Expected value of xn square. Okay. Let me write a few more terms. Well, I hope this matrix is familiar to you. The reason is, previously we have decided to consider this as some kind of an inner product, isn't it? So this is nothing but the inner product of x1 and x2 random variables defined in this fashion. Okay? Well, then this becomes, you may say, the matrix of inner products. This is called actually, what do we call this matrix? A Gramian matrix, isn't it? If I define this, or if I think about these expectations are as inner products. Okay, so this becomes, one more time, the correlation matrix. Okay, now how about this one? So this one is almost like the same. So let me skip this intermediate step. So this is equal to expected value of x1 minus the mean of x1 parentheses square. Okay, so the only difference is that now I have x1 minus the mean of it, x1 minus the mean value of it over there. So if I multiply them, I get the square and expected value. The second entry, expected value of x1 minus the mean of the first random variable, x2, this. Okay, and the last one is, so let me write the last one over here, expected value of x1 minus x1 mean times, well, let me write it a little smaller. Well, let me write it like this then, covariance of x1 comma xn. Hope you will agree. Now this one is, okay, covariance of x2 comma x1. This one is covariance of xn comma x1, and so on. This is the first column. xn comma x2, and the last one is, so this is, you may say, the variance of xn. So what's going on? Well, if I multiply, well, let me write this vector. This is x1, random variable, minus the mean of it, the mean value of x1. x2, random variable, minus the mean value of this. Okay? I have this. So transpose of this is over here. And this goes like this. This goes like this. Okay, so if I multiply these two vectors, the 1 entry of this matrix is product of these two. And as you see, I can put this capital if you wish, then I get this. So what do you recognize for this one? This is what we call the variance of, you may say, x1. Okay? So similarly, now this one, the first one times the second one. So if you check this, this is the definition of covariance of x1 and x2. So I was running out of space when I was calculating the entry of this times the last entry of this vector. But simply I have written as covariance of the first random variable and the nth random variable. Okay? Covariance of first random variable and the nth random variable. So no surprises, this matrix is called covariance matrix. So what do we see? Now, if I have n random variables, I calculate the pairwise covariances, okay, of every, let's say, pair of that vector and list it in this matrix. This is called the covariance matrix. And this is the systematic way of calculating that covariance. So sometimes in signal processing, in most of the cases, these random variables will be zero mean. So it will be equal to, this will be equal to 0. So I get this. And obviously, covariance matrix reduces to the correlation matrix. Okay? Now, all of our discussions about the linear dependence between x1 and x2, x1 and x3, now they extend to pairwise interpretation of every entry of this matrix. Okay. Now, let me write some properties of this covariance matrix. Properties of covariance matrix. Number 1. So the first property is this is a Hermitian symmetric matrix. So what's the meaning of this? If I have Cx is equal to Cx Hermitian, okay, for the complex case, Hermitian symmetric matrix. So what is the meaning of this? Well, let me finish this and then we can discuss. Positive semi-definite. That is Cx is, this is our notation, greater than or equal to 0. Okay. What else? Since this is Hermitian symmetric, it comes with some additional, let's say, eigen properties, but we can discuss them later on. So let me say on 1, well, definition of the Cx is expected value of, let me do it for Rx because, you know, it's very simple. They are very simply related and I don't want to write this long thing again and again. Okay, Cx or Rx. It's almost like the same. So this is x times x transpose, okay, as I have said. But if I have complex valued cases, complex valued vectors, then this is for real valued vectors. So the definition is, now you replace these transposes by Hermitians, okay? Then Rx, expected value of XX Hermitian. Okay. So this is the Hermitian operator. So this is transpose and conjugate. Okay. Now how about this? If I take Hermitian of this is for complex valued vectors. Okay. Complex valued vectors. Now if I have Rx of Hermitian, so how can I calculate this Hermitian? Now I want to calculate the Hermitian of this matrix. Well, the issue is this. Can I move this Hermitian inside of this expectation operator? Well, if you think about our process, I generate this matrix, then every entry of this matrix is taken into account by this expectation operation. Okay? So I can do the following. I generate this matrix, take its Hermitian, and then finally I do the expectation operation. Do you think there will be a change? There won't be a change because this Hermitian operation or this transpose operation is just changing the places of these entries of this matrix. So expectation operation can be applied before and after. It doesn't matter because it's like a, you may say it's like a geographical location. I am changing the geographical locations. So that means that I can move this Hermitian inside of this expectation operation. So this is equal to x Hermitian inside of this, I have that. So clearly I have x Hermitian one more time, so I get Rx. Okay. So what does that mean? These two entries in general, if they are complex valued, 1, 1, 2, 1, they are complex conjugates of each other. Okay? And on the diagonal, no surprises, they are real valued because, you know, on the diagonal I have variances actually. They are always real valued. Okay, so how about this second one? 2. Positive semi-definite. Well, let's apply the definition. Z transpose, let's say, or let me write Hermitian. Z Hermitian. Let me use, you know, again, Rx times Z. Is it greater or equal to 0? For all Z, is it, I don't know, other than the 0 vector. Okay? Is it strictly non-negative, this quadratic product? Is it strictly non-negative? Well, let me process this. This is equal to Z Hermitian expected value of, this is Rx, x times x Hermitian Z. Okay? Now, how about this? Please remember that this is an expectation over x, random vector x. This random vector x. So how about this? Can I move this, you know, z inside of this? Can I change the places of expectation operation and this linear combination? Okay. Well, okay, let's do this and then think about it. So if I move one of them first, then the other, I can move the other one. So this is, I can do them sequentially if I can convince myself that this is possible. This is equal to this. And what I see is this. This is the expected value of x Hermitian z. This is the magnitude square of this complex number. Okay? And this is always greater than or equal to 0. So what's going on? So after this operation, so what is this? Is this a vector? Is this a matrix? Or is this a scalar? So this is just a scalar, am I right? Because this is a row vector, this is a column vector. So about this is another scalar, but this scalar is the conjugate of this scalar, okay? They are conjugates of each other. So this is the reason that I have magnitude square of this, okay? Maybe, let's put it like this, magnitude square of this quantity is greater than or equal to 0. Now how about this? Again, this expectation operation is like the ensemble average. So maybe I can first linearly combine this x vector with z vector, elements of this random vector is the random variables. I can combine these random variables by this z vector, and then at the end I can evaluate the expectation. Is it possible to do this? Well, assume that this is just like a simple case, like it's 1 by 1 case, then this will be just a scalar, maybe it's 2. This is another 2. So you can move these constants in, as you see. Okay? So this is the same idea. If I have a constant vector over here, I can move this constant vector in. Then I can evaluate the expectation and then process it. Okay? Because it's a constant vector, not affecting this expectation calculation. Well, that is the reasoning. Okay? So we see that indeed this is positive semi-definite. So what's the meaning of this? We have some news. So this means that eigenvectors of Cx are orthogonal. Am I right? Eigenvalues from our previous discussions are real. Okay. How about this one? This one says that eigenvalues are non-negative. So immediately, because of these properties, I have these other blue properties also, but they are the implications of these. Okay. Of course, they are equivalent, but these are the general properties, positive semi-definiteness, and so on. Okay, now I want to discuss right now. So what we have seen right now a pairwise interpretation of entries of a random vector. Okay, pairwise interpretation. So of course you can say that why don't we interpret them not in terms of pairwise but in terms of triplets? Okay, that's also possible. That's called higher order statistics, but that is not a simple thing to do. So this is much more basic than, erase this part also. Okay, so this is called, that's called, if you interpret the elements of this random vector x in a triple way, or four random variables together, okay, then that becomes higher order statistics, and it's more like a research topic than a basic, introductory knowledge. Now I want to discuss, right now, the Gaussian distribution. Okay, so in the definition of Gaussian distribution, you will see that this covariance matrix, the mean vector, will come up. This is the reason that I want to discuss this Gaussian distribution at this point. So let me say, let's say 1D case. You will appreciate it later on. Why do I call it 1D? So let's say that x, random variable x, is n mu, let's say sigma x square. Okay, so this is called normal distribution, as you can remember, with, this is called the mean value, and this is of course the variance, okay, of this. So what does this say? This says that the Gaussian distribution has the PDF, probability density function, in this form. Let me call this mu x then. So this is the mean of this x random variable. So I have such a case. I am sure that we are familiar with this because this is the most famous distribution coming up in all of these studies, in several, let's say, statistical concepts. Mu x, this is x, fx of x. Okay. So how do I interpret this Gaussian distribution? Well, some interpretations. So you see that this exponent is always positive. Sorry, always negative because of this, but this quadratic term is always positive. Okay, obviously. So meaning that for large x values, I get very small, or for this side, for large x values in, let's say, in magnitude, I get very small values because of this exponential behavior, decaying exponential behavior. Okay, so if there is a maxima, where is that maxima? So I'm looking for the maxima of this in terms of, I'm optimizing with respect to x, let's say. So if there is a maxima, then this maxima should be minimizing, so maximizing this exponent, or it should be minimizing this quadratic that you see over here. What is the minimum of this quadratic at mu x? And that is it actually. This is the maxima. Okay? It takes a value according to, this term. So how do I interpret this? So this is, well, we haven't said so, but if this is the density, random variable x, according to this density, Gaussian, let me write x distributed n mu x sigma x square, then no surprises, this is the mean value mu x. Okay. Well, from this sketch actually, you can also immediately see this is true. Well, okay. So what happens when sigma x square changes? So you can see when the sigma x square is, let's say, larger for the same mean value, or maybe it's like much smaller, okay, something like that. So this is sigma x squared 3, let's say, for the third random variable. This is sigma, there is a second random variable. All of them are Gaussian distributed, and as you see, this is the first one, this. So what happens if I increase this variance? So this is, let me write. So what I see is that the blue one, the blue one has the smallest. The blue one has the smallest variance. So what do I mean by that? Well, the interpretation of the variance. So expected value of x minus mu x is sigma x squared, isn't it? That is the definition of the variance. So for this distribution, if you calculate this expectation, then you get this parameter. Actually, it's a little confusing at the beginning because these two parameters of this distribution, normal distribution, they are also the first two moments of this distribution. So it's just a coincidence, you may say. So these are the parameters of the distribution, but from the parameters, by looking at the parameters of the distribution, I can get these expectation results without any operations. Okay, we can show how this is calculated and so on, but so if we think about the variance, assume that this is true. Now you see that this random variable, it has a spread. This is also interpreted as spread. So the blue one has, let's say, this is called maybe 1 standard deviation, isn't it? So this is sigma square root of variances standard deviation. You see that 1 standard deviation, this is like 60% of this probability. Okay, so the area under this is like 60. So you see that 60% of the time you are limited to a small interval in comparison to the other ones. Okay, well, this is also not correct, I guess. So let me correct this. x2, which one is which? So this is wider. X, I want to have 1 for this. Sorry for this. So this one has spread smaller. Okay. The black one has spread this much, let's say. So 60% of the probability around the mean value is in this interval. And for the red one, 60% of this lies in a much wider interval. Okay? As you see. Okay? So you see that now the variance for the blue one is smallest, second smallest is black one, and the largest is the red one. Okay? That is it. This is the variance interpretation. Well, the mean value and the variance, they are extremely important for, as you see, for the Gaussian distribution. Now, if I have, let me see, if I have n-dimensional case, what would I say about that? If I have, n-dimensional Gaussians. So what's the meaning of this? Now I have x1, x2, up to xn. Okay? So this is a random vector, x. So this is joint distribution of let me write x1 up to xn. So we say that x vector is jointly Gaussian distribution, jointly Gaussian distributed. So what's the meaning of this? If it has such a density, fx, x1, x2, xn. Okay? So how do I write this? This is equal to 2 pi to the power n. Then I have cx, determinant this. Okay. 1 over e to the minus x minus the random variable x. Okay. X minus mu x transpose cx inverse x minus mu x. Okay. Now this is a little bit intimidating looking. So this is an equality. So it is equal to this. So this is definition for jointly Gaussian. Jointly Gaussian random variables. Okay. Let me check this if I make a mistake or not. Okay. There is 1/2 factor over here. And that is it. Sometimes we write this a little bit more, this equivalent, 2 pi to the power n over 2. It's a little, better looking because you have n over 2's over there. Now, let's see. Does this thing reduce to this case when n is equal to 1? Okay, at least it should be compatible, isn't it? So when n is equal to 1, so this is what? Well, Cx. What is the Cx? This is the covariance matrix that we have previously defined. How about this mu x? So this is the mean vector. Okay? Covariance matrix. Now, if this vector is 1 by 1, or it's just one entry, okay, then this is x minus the mean value. Okay. How about this? The first entry of this matrix, 1, 1 entry of this matrix is the variance, isn't it? There is only one variable, variance of x. So you take the inverse of this. So 1 over variance, and there is a 2, 1 over 2, and very good, then I have a square over there. Okay. How about this one? 2 pi 1 over 2. 2 pi 1 over 2 square root. How about this? Now I have, so this is the determinant of Cx. This is a matrix. Determinant of Cx. Unfortunately, it's a little complicated looking, but we don't have to worry about the details so much because this is just a constant, for example. Okay. So in the 1 by 1 case, this matrix is just 1 by 1 matrix, so it's just sigma square. So you have sigma x square root over here. So you have compatibility with, as you see, one-dimensional case, no problems. Okay. Now, if I have such a definition, let's accept this definition. It's a little interesting because as you see that we are immediately generalizing familiar concepts of mean variance to mean vector and the covariance matrix, as you see. Okay? I am doing this generalization. So let me look at this two-dimensional case more specifically. So this is n-dimensional. In the two-dimensional case, I need to think about vectors with 2 entries. And this covariance matrix is 2 by 2. This mean vector is 2 by 1, and that is it. So let me write then, if I assume x1, x2, 2 random variables, then the Cx is equal to, so this is sigma x square, covariance of x1, x2. This is covariance of x2, x1. This is, let me move this. I have this. So this is my Cx matrix. Okay. So instead of this one, what can I write? I can write from our earlier discussion. Well, I can write the correlation coefficient. Okay. I can write Rx1, x2, correlation coefficient of x1 and x2 times sigma x1, sigma x2. Okay. Well, the reason is, this is the correlation coefficient. Remember, Rx1, x2 is covariance x1, x2, sigma x1, sigma x2, because this is correlation coefficient definition. Okay? Correlation coefficient, this is the definition of the correlation coefficient. So I need the covariance. So covariance is, as you see, correlation coefficient times product of standard deviations. So this matrix is something like that. So I have the mean vector that is easy to handle. So if I write this, then the joint density in terms of two variables, x1 and x2, I have 2 pi determinant of this matrix times e to the minus x1, x2 times this matrix sigma x1 square, x2 square. So this is r x1, x2, sigma x1, sigma x2. And I have the same number over here because it's a symmetric or Hermitian symmetric matrix, as you see. Since I'm talking about real quantities, so it's just symmetric. So I have something like that. So this is, let me move this a little over here. 1 over 2 pi. So this is exp. Let me write it like this. Okay. I have something like that. So this is the same as this one. This is the same entry. Now, what do you think about this operation? So let's think about this function. Okay. Oh, by the way, I have taken mean vector as 0 over here. Okay. So I have taken this mean vector as 0. I have this. Now, if this x vector is taking very large entries, what will happen to this exponent? Do you think it will blow up? So I get infinities and so on? Well, the issue is the following. Now, this is this term. I have, again, x transpose, a matrix, Cx inverse times x in the exponent. So this is this exponent. Okay. Now for this exponent, what do I know? Well, what can I say about this quadratic term? So since Cx is positive semi-definite, so I know that Cx inverse is, well, let's say positive definite, is also positive definite, because if it is semi, I cannot take its inverse. Okay. Assume that it's positive definite, then that's also positive definite, meaning that this quantity is always positive. So meaning that the exponent is always, if this is always positive, it's always negative valued. So for very large x values, again, this will be like in this case, it will be approaching 0 for very large, make this time very large normed x vector and very large normed x vector in the other direction also. This will be taking very small values because this is always positive and I'm taking an exponent of a large negative number. Okay, so this is nice, it's not blowing up. And as you see, we need this positive definiteness of the covariance matrix immediately in this discussion. Again, where is the peak value of this? Now the peak value of this is, as you can imagine, the maxima is the minima at this point, and this is always positive. So when the x vector is equal to 0, I have, the maxima. So that is, as you see, the mean vector, the location of the mean vector. So in general, of course, this is written as the exponent minus 1 over 2 x minus mu x, x minus mu x. I have something like that. So if you try to maximize this quantity, then I'm minimizing this part. Since this is positive definite, the minimum is x is equal to the mean vector. Okay, that is it. So very similar to this case, as you see. Of course, this reduces to this case when n is equal to 1. So this becomes a generalization of those scalar ideas to multiple variables, as you see. Okay. So what else? Let me erase this part. So let me say level curves. So I want to understand, at least in this two-dimensional case, for example, this is equal to C1. So let's say that this is my density, Gaussian density. So the locus of the points for which this density takes the value of a constant, C1. So, you know, what are those points? Now you can immediately say that if this is equal to C1, then x minus mu x, this quadratic term is important. Cx inverse x minus mu x should be equal to another constant, okay? Let's say d. So the reason is, in this density, as you see over here, these are just constants. So if I equate this part to c, then I can do this multiplication. Then I can take the logarithm. Then I can multiply by -2 both sides. So this is equal to, this quadratic form should be equal to another number, okay? If this is equal to C1, then there is a D1 value for which, when this is equal to D1, I get automatically this is equal to C1, okay? So I need to again understand the level curves of this quadratic. So this is the reason that previously we have studied quadratics, okay? So the level curves of this. So in general, we have, in the two-dimensional case, let's say this is mu1, mu2, then we have the center. We have such level curves. These are not very well drawn, but they are supposed to be some ellipse-like curves. Mu1, mu2. So this is x1, x2. So how about this? So this is the locus of points. Let's say that this is equal to C1 is this, okay? Locus of these points. So what can you say? So for this one, I will explain this a little bit further later on. This is in ellipsoid shape. So this is called the major axis of ellipse. And this is called the minor axis. Minor axis of the ellipse. So major axis means, you know, this is longer in this side and this is smaller in this side, okay? So we have a situation like that. So how about this part? This is the location, so I'm sketching this. This function takes the value of, as you see, 0, okay? So this function takes the value of 0 at this point. How should I write this? So this is fx x1 x2 is equal to 0, okay? So let's say that this is the point for which this function takes the value of 0.1. So over here it's always 0.1. This is like 0.3. I'm just making this up. This is like 0.5. So on this line, the outer ellipse, I have always 0.5s and so on, okay? So please consider this. If 0.1 is sketched as the height about this line, so there is a dip point over here, and it's like increasing like this. But if you cut it at this, you know, z-plane, you get these ellipses, okay? Well, what does that mean? Well, this is the level curve. So for the Gaussian distribution, you can imagine that this becomes, because it's in the exponent, this becomes the peak point of this Gaussian distribution, and they just, if you go away from this mean vector location, it just decays down exponentially, okay? Because, for example, if this is 0.5, then you have exponent -1/2 0.5, okay? Times a constant value, that becomes the value of the Gaussian distribution. So this is the interpretation of level curves for this quadratic one more time. Now you may wonder, how can I have ellipses and, you know, this major and the minor axis of the ellipses? But let me say a few things. Well, assume Cx for now is diagonal, okay? if I assume Cx is diagonal. So what is this one? And let's do not worry about the mean vector. Okay. Then X transpose Cx inverse times X. So this becomes what? So this is X1, X2, X1, X2. Am I right? But there is an inverse over here. I have zeros also. So this is equal to X1 over sigma X1 square, X1 square, X2 square, sigma X2 square. Because previously we have studied how we calculate these quadratic products. So this term, after taking this inverse, becomes 1 over sigma X1 square. And then this term is multiplied by X1 and X1 square. This term is multiplied by X1 and X2, and so on. So this is my function. Okay? So I am looking at the locus of the points for which this is equal to maybe D1. Okay? So I'm equating this to D1. So I have 2 degrees of freedom, X1 and X2. So how can I sketch this? Okay? So if I do this sketch over here, let's say. So no surprises. This is symmetric with respect to origin. It's symmetric with respect to X1, X2 axis. It's a very symmetric. But let's say that this is equal to, let's say D1. Then I get an ellipse like this. So this is the equation of an ellipse, maybe you can recognize. Okay? So now I'm equating this to D1. When X2 is equal to 0, X1 square should be equal to, this is a mistake, D1 times, okay, let me write with another color. So this is D1 times sigma X1. This is minus D1 times sigma X1. And this point is minus D1 times sigma X2. And I have this. Okay. Again, I'm equating this to D1. When X2 is equal to 0, I'm on this X1 axis. So I see 2 points, D1 times, sorry, square root of D1 times sigma X1 and so on. Okay, I have that. So if sigma X1 is much larger than the other sigma X2, so you see that this axis of this ellipse is longer. This is called the major axis. Okay? If sigma X2 is smaller, then this part is smaller. This section is smaller. That part is called the minor axis of this ellipse. Now, a special case. So if Cx is equal to, let's say that these sigma x1 is equal to sigma x2, then I have identity times variance as my covariance matrix, as you see over here. Now, if this is the case, what are the level curves? So level curves for this one is right now they are just circles at the origin, as you see. Okay, that is it, because this is equal to x1 square over sigma square plus x2 square over sigma square. If you equate it to d1, let's say, you get a circle. Okay. Okay, so we have at least have some understanding of this major axis, minor axis, and their relation with, as you see, variances. Okay. So later on we will explain why this is rotated a little bit or not. Now some facts on, let's say, multivariate Gaussians. So if, let's say, marginalization so if, let me write it for two random variables. If x1, x2 jointly Gaussian, or let me say for all xn jointly Gaussian, then its marginals x1, let's say xk, k1 to n, are also Gaussian. But obviously, as you can see, this is a one-dimensional Gaussian, this is an n-dimensional Gaussian vector. Okay? So similarly, let's say pairwise, if you have xk, xl pair is also jointly Gaussian. So I'm not proving this, but its proof is not very complicated. And what you need is, the simplest proofs for this one is using moment generating functions, okay? For multiple variables. Then you do a substitution in the moment generating function. For example, you have moment generating function for the joint distribution of n random variables. So that moment generating function has variables s1, s2, sn, let's say. If you substitute in the final result s2 is equal to 0, sn is equal to 0, you get the moment generating function of the marginal. And when you look at that expression after substitution, you get the Gaussian's moment generating function. So proof is, if you do it in that way, it's very trivial. Okay. Now, after this marginalization property, we can say interesting things. For example, if I tell you that my covariance matrix, so let me have an example. If x is x1, x2, then covariance matrix of x is, let's say 3, 3, 2, 2, something like that. Okay? And the mean value, the mean vector of x is, let's say 10 and 2. Okay, now here's a question. What is, find density of, let's say, x1 only. So how can I find the density of x1? Okay. Well, from this fact, you know that the density of the x1 is Gaussian. Okay. So to define a Gaussian, what do I need? So to define this Gaussian, I need the mean value of x1. So do I know the mean value of the first entry of this vector? Well, I know this. I'm sure it's Gaussian. So its mean value is 10. Can you say anything about its variance? Let me make this a little different, 5. Okay. Then, what is, this is the variance. Okay. So this is x1 distribution. It's Gaussian distribution according to that. x2 is, the mean value of x2 is 2, its variance is 5. So by just looking at this 2, general information about the joint distribution, I can immediately say the marginal densities. Okay. So if I have a bigger matrix, okay, meaning that covariance matrix is, let's say, 5 by 5. I have several entries over there. And if I'm interested in the joint density of the x1 and x2, then I'm looking at this part of 2 by 2. x1, x2 part of this covariance matrix and related entries. So I get this, marginal density of this pair immediately by observing from the covariance matrix and, the mean vector. That is it. So this is a very important property. and it simplifies our life significantly. Now how about the next? Linear processing of Gaussian vectors results in another Gaussian vector. So what's the meaning of this? Well, if I have x, so this is Gaussian vector with distribution, let's say this, and covariance matrix Cx. Okay, so as you see, this is a Gaussian this time vector with mean vector and covariance matrix this. Now, let's say this is an example. So let's find, use this result, m times x. Okay. So let me call this y. So y vector. Let me write this just y. Let's find the density of joint density of y vector. Okay, joint density of the y vector. So how can I find that? Well, let's also accept that as it is. Linear processing of the Gaussian vectors results in another Gaussian vector. So the question is, now I know that y is distributed with, this is a Gaussian vector. This is, but I don't know the mean vector and I don't know this covariance matrix after this transformation. But how can I find them? Well, let me give it a try. Then expected value of y, so this is mu y, is equal to expected value of m times x. Okay. Again, because m is just a constant, you can take it out. So it's not a random quantity. This is a linear operation. So just summations and multiplications. So this is possible. So this is mean vector of x. So very nice. So mean vector of y is, as you see, simply found. So this is the mean vector of y. No surprises. So let me find the covariance matrix. Cy. Okay. So this is expected value of, well, y minus mu y, y minus mu y transpose. Okay. But as I have said, without no loss of generality, I may assume that for now, this mu y is equal to 0 vector, because this covariance calculation does not depend on the mean. So just for simplicity, let's assume, I can assume at this point, this is a 0, because as we have discussed before, this bracket is always a 0 mean vector, this bracket is a 0 mean vector. So whatever the mean is, it's always subtracted out at the first step. So I have little space over here, so let me try to cover it at this point. So this is, y times y transpose. Okay. So what is y? M times x. So let me write it over here. Okay. So this is expected value of mx and the transpose of this, x transpose m. So transpose of this is x transpose m transpose, as you see over here. Okay. Now, if I do this, again, I'm taking these constant terms out. M times x transpose m transpose. Okay. This is a matrix. And my final result is M times, this is Rx M transpose. Okay. Or this is Rx, but I can call this Cx also, because I have assumed, zero mean. Okay. Zero. I have assumed all of these mean vectors are zero, so I get this. So how about this one? Cy is then? Then this Cy is equal to M times Cx times M transpose. Okay. That is it. Very happy, because it turned out that I can get this Gaussian distribution after this processing very easily. Okay. So this Gaussian distribution, because its parameters are this Gaussian vector, this mean vector and this covariance matrix, if I can calculate these two parameters, which are also the moments of the distribution as you see, I'm done. There is nothing else to do. Again, we need to show this linear processing of Gaussian vectors results in another Gaussian vector, but we are not doing so. Actually, this is one of the definitions of the Gaussian, even the processes and so on. So let's accept this as some facts, okay? Some facts on Gaussian distributions. So one more example then. And we will be done with this hour. So previously we had an example, variance of xi is calculated. Variance of summation of xi, I1 to n. This was one of our earlier examples. Okay. So how can I calculate this xi's over here, are random variables? Okay. So previously we had a solution, but let me think about this way. Now, this is solution number 2. X vector is composed of this. So x1, so this is an m by n vector. Now, how can I calculate the variance of x sum, their sum? So let me call this a z variable, z. Z is equal to 1, all one vector, times x1, xn. Okay? So this is the sum as you see. So I can briefly write this as 1 transpose times this x vector. Okay. So now the question is the variance calculation. So for the variance calculation, as I have said, the mean values have no importance. So without any loss of generality, let me write it, without any loss of generality, assume xk means are equal to 0 for all k, for all of them, okay, for all k. Because, as I have said, this is the variance calculation. Whatever the mean is, it will be subtracted out at the first step. So, I want to calculate, if this is the case, then this is also 0 mean. Then the variance of I1 to n is, so this is the variance of z, am I right? And the variance of z is expected value of z squared, because z is also 0 mean. Okay, the mean of z is also equal to 0. So how can I do this? Then I should, let me use this. Well, what is this 1 transpose? So this 1 is again a column vector. After you take the transpose, it becomes a row vector. And it's composed of all ones, as you see. Okay. So this is 1 transpose x. So let me write z one more time. Now it's z square. Okay. Let me take the transpose of this. Let me because it's just a scalar, because this is Z, as you see, summation of these things. Now, if I take its transpose, okay, let's put this. Then I get 1 transpose, expected value of Rx, expected value of X transpose 1, which is equal to 1 transpose Rx and 1. Okay. So what is this? Well, 1 transpose Rx and 1. So this is all ones. Well, this is Rx matrix. Okay. Expected value of x1 square, expected value of x1, x2, expected value of xn square, expected value of x1, xn, so on. And once. So I'm adding up all of the entries of this matrix. Okay. That is it. So if these, random variables are not zero mean, then instead of this matrix, I'll be writing here Cx matrix, meaning that instead of this Rx, I'll be writing here Cx, and the final result is the variance of I1 to n, xi is 1 transpose Cx and 1. Okay, that is it. So we are adding up all of the entries of this covariance matrix, as you see in this calculation. So what we have seen? What we have seen is the vector processing. Now I'm considering these random variables not as individual quantities, but elements of a vector. Once I consider them as an element of a vector, then I can do linear processing very easily, as you see. So I can calculate mean, covariance calculations, linear operation on these so easily. So for example, if these xi's are jointly Gaussian distributed, I know that after linear processing, this will be also Gaussian distributed. Let's assume that their mean is, all of them have zero mean, then their sum is also zero mean. How about their variance? Their variance is, well, this. Okay, very easy to say. So from here, I can say that the random variable z, which is their sum, is Gaussian distributed with mean value 0 and variance this much. Okay. So vector processing enables us to say things like that. Okay, thank you very much. We will continue.